Okay, I'll be back in a second. Should be at least one more press.
Okay.
Probably one more. Try to wait for him. What is this camp you're going to?
It's called Awesome Math. It's a competition preparation camp. So it'll help on like the AMC tests
I see.
and the AE tests.
Where is this?
Well, they have like 5 locations across the country,
Mm-hmm.
but the one I'm going to is in New York.
Hmm.
So
I
it's
see.
at Cornell University.
I see. Pretty cool.
Yeah.
When is it? When are you going?
I leave on July 13th. Right when everybody else finishes.
It's okay. I think we should start then.
Yeah.
Okay. Okay. Hi, everybody. We have very few people in here, but still we're gonna go through. I mean, there was a bunch of people who did the Olympiad lecture. They're just not here. Okay, so let's go through the problems. You did A, right?
Yeah.
So let's do number 1. Okay, so many people did this correctly. So the point is that when an hour hand moves by alpha degrees, at the same time, minute hand moves by. Hey, there will be only 2 of you here today. So have a seat somewhere in front. I mean, there were more people who wrote the Olympiad, but everybody's in some kind of camp. Okay, so when our hand moves by alpha degrees, minute hand moves by 12 alpha degrees. Right. Did you do A or B?
B.
Oh, okay, so you have one of this. Okay, this means that the first time the hands will meet again will be when 12 alpha will be different from alpha by 360 degrees, from which alpha is 360 over 11. And then if you want to express it in hours, well, 12 hours is 360 degrees, so you need to multiply it by 12 over 360. So 1 and 1/11th hour from midnight or whatever, the two hands will meet again. Okay, so this was meant to be not a super hard problem. It was a super hard. Okay, so the second problem. We have A1 minus B1, etc., A7 minus B7, where B's are some permutation of A's. We want to show that it's even. So the easiest way to argue this, I know, is as follows. You just say that it's odd if and only if each factor is odd. And this happens if and only if AI and BI have different parity for any I. Meaning one is even if and only if the other is odd. But because B's are the same as A's in some other order, this means that number of even A's is equal to number of odd A's. Right? Because number of even A's is equal to number of odd B's, which is equal to the number of odd A's because B's are the same as A's. But that's impossible because there's total 7 of them. And that's a contradiction. So some people wrote that there must be at least 4 of one parity. So maybe there is, for example, at least 4 odd A's, even. But then no matter how you put 4 odd O's downstairs, there will be at least one overlap. And similarly, if there was at least 4 even ones. And this works. I prefer the first method, but this also works. Okay, any questions about this? Let's see. No question. Okay, so now let's go to 2 slightly harder problems. Question number 3 was, if you have 2 triangles and every side of the first one is bigger than every side of the second one, is it necessarily true that the area of the first one is bigger than the area of the second one? The answer is no, first of all. So there are people who try to prove that it's yes, so that's immediately false. And the easiest way to argue something like this, so if you need to prove something is true in general, you need to actually give an argument in general. But if you just ask some question like this and the answer is no, it's really easiest often to just give an example. So to solve this problem, it was enough to just give an example of when this is false. So here's an example I came up with. So let's take this triangle with sides 24, 13, 13. And really there is a lot of freedom in how to make an example here. So what's the area of this triangle? We can compute the height. It's by Pythagoras theorem, it's 13 squared minus 12 squared square root, which is 5. And then the area is 1/2 times 24 times 5, which is what? Which is 60. And then we can take another triangle, which let's take a regular triangle with side length 12. Right, so then each side here is bigger than each side here. But the area will be, the height will be 12 times square root of 3 over 2. So the area will be 1/2 times 12 times 6 square root of 3, which is 36 square root of 3. And now we just need to argue that 36 square root of 3 is bigger than 60. Do you know how to argue that? I mean, yeah.
Divide by 12, so it's 3 squared 3 is bigger than 5.
Yeah.
Prove it's bigger than 5 thirds.
Yeah, so it's the same as 3 square root of 3 is bigger than 5.
And then just prove square 3 is greater than 5.
Let's square that. So that's 27 is bigger than 25, which is true. Okay, so in this problem, it was just enough to give an example. You could imagine an argument where you some could generally argue this, but it's sort of, it would be actually quite hard to make such argument without giving an example. So it's really the best to give an example. Okay, let's do number 4. So number 4 turned out to be much harder than I thought. I thought people would really easily do it, but many people had trouble doing it. So here's a proof. So what was the problem? So first of all, some people had trouble understanding it. So we are given 8x8 board, and we are told that any 2x2 square has cells of different colors. There are 4 colors, right? So if you whichever 2x2 square you pick, there will be colors and 1, 2, 3, 4. 4 different colors. And we asked to prove that the 4 corners of the square have also different colors. So first of all, why did I say pairwise different? Because so usually this expression is used to be in unambiguous. So like let's say you have 4 things and 3 of them have the same color, but the 4th one doesn't. Do they have different color? And one could argue that yes, because not all of them have the same color, therefore they have different color. So that's why just saying proves that those bunch of objects have different color is a bit ambiguous. So that's why to be unambiguous in Olympiad problems often is used to say pairwise different, meaning that in each pair the colors are different. Okay, so this was a problem. Now the solution. So first of all, it claims that it's true for any, say, 2m by 2m board. And proof is kind of by induction. So first we will prove that true for 2 by 2m boards. Why is that? Well, if you have just 2 by 2m board, then if you start with colors, let's call them 1 and 2, those will be 3 and 4 in some order. Those again will have to be 1 and 2. They will either be 1 and 2 or 2 and 1. And then the next pair will have to be 3, 4 or 4, 3. Etc. And then those will have to be again 1 and 2 or 2 and 1. So So we see that in each odd location, they have to be 1 and 2 in some order, and in each even location, they have to be 3 and 4 in some order. Therefore, the last location, which is 2m, which is even, they will have to be 3, 4, or 4, 3s. 3, 4, or 4, 3. And therefore, they all will be of different color. Okay, so this is, but once you know this, and then you can prove it for the whole board like this. Like, let's say we pick this 2 by m. The colors are 1, 2, 3, 4. Then let's consider the next 2 by m, or 2 by 2m. Since those colors are 2 and 3, and we know this lemma, then those colors will have to be either 1 and 4 or 4 and 1. And the next colors will have to be 2 and 3 or 3 and 2, etc. So each one will be 1, 4 or 4, 1, and the next one will be 2, 3 or 3, 2. So at Zen's, because there will be total even number of them, this one will be 2, 3 or 3, 2, and therefore all corners will be different colored. Okay, so several people try to do some kind of inductive argument, but it was much more complicated than this, and I'm not sure it actually worked.
What about the proof by contradiction?
So
I tried like a proof by contradiction, but I screwed it up because I just worded it incorrectly.
right, so yeah, I'm actually curious what you really meant by that.
So you start in the top box, and we're trying the whole time to make it so one corner has the same color as the top corner, and we realized that we can't in the first column as we travel down for the even spaces. It's similar
It's
to
using the same
what you did with the
Right.
lemma.
So in some sense, so I can see how you can easily argue that this color will be different from this color. And you basically use this, right? Because you take the 2 by something.
And then you realize.
But how do you show that those two are different? Right?
No, so what you do is you try to make them the same, and then you realize that the problems that arise when you do that.
But you cannot just write, I tried to make them the same and I failed. Because people will just say, well, you didn't try hard enough. Like,
Well, it's the only way to do it.
No, I mean, I did it without it, right? I did everything without saying I tried to make it and it didn't work.
You need to basically find a square such that they do have the same two colors. They contain the same color twice.
I mean,
Let's say you got a contradiction.
there could be many different ways to solve this problem, but you do want whatever you write to be a rigorous argument which considers all cases. Right, so somehow the grader will never just buy that, here's I tried this and it didn't work, therefore it doesn't ever work, right? Because they will be like, well, we didn't try hard enough, maybe.
How do you actually word that? Not like your argument. Like, do you say you go upwards? Like, consider each 2 by 2, 2 by 2m.
So this was an induction, right? In some sense, base case was
Yeah, I get that part.
2 by 2, and then the general case was 2 by 2n. And then you could state this argument also as induction, right? The base case was 2 by 2n, and the general case is 2m by 2n. So in some sense, you could just say that it's an induction. Okay, let's do B problems. Okay, number 5. You have 2 circles. You have a tangent line. You want to show that the sum of those 2 angles is 180. So all you need to know is the following lemma, which is, again, very famous. This is just part of the standard angle changing technique. If you have a circle and a tangent and something like this, then this angle is equal to this angle. I mean, for any point on this arc. So how do you apply it here? Well, you have what? Let's draw this line, and then we know that this angle is equal to this angle, and this angle is equal to this angle. Therefore, when you sum this angle and this angle, you're just summing the angles of this triangle. And therefore, it will be 180. Right, so this is from the same kind of class of theorems where
So is
those angles are equal to each other.
Is there a name for that, or can we just assume it?
So this one is a well-known fact.
Yeah, but do we need to like cite the name of it?
That's
or,
a
like,
good
write it
question.
as a
I
lemma?
don't remember
Tangent.
what's it's called in English, right? So it's a you can
You could
almost say
probably
it's
just write that.
the angle between a tangent and a chord is equal to half of the angle measure of the arc of this chord,
Yes.
which is also yeah. So basically, you somehow need to. I mean, I'll need to look it up how to refer to it, but yes, it is a well-known fact which could be assumed during an Olympiad. Okay, let's. Move on. So there was an inequality. So you were told that ABC are positive real numbers such that ABC is 1. And you asked to show that the following thing is at least 3. So we asked to show that it's at least 3. So first of all, when writing solution of inequality, I strongly recommend just start with the inequality itself and start transforming it. I mean, on each step you need to do something so that it's an if and only if statement. But like some of you wrote solution where you started with something obvious and you try to transform it into this, which can be very painful to check, and it's easy to make a mistake, etc. So let's just start with this left side. And here's what I'm going to do. I'm going to substitute for those ones. I'm going to write ABC. So I'll write ABC plus AB over 1 plus A plus ABC plus BC, 1 plus B, ABC plus AC, 1 plus C, which is AB 1 plus C over 1 plus A plus BC 1 plus A 1 plus B plus AC 1 plus B 1 plus C. And now we can use the famous arithmetic geometric mean inequality. This is greater or equal than 3 cubic roots of their product, which is A squared, B squared, C squared. And this is basically 1, right? It's 1 plus C, 1 plus A, 1 plus B divided by 1 plus A, 1 plus B, 1 plus C. Those cancel out, and this is 1. Therefore, this is just 3. And we are all done. So some of you did it slightly differently.
I applied it right away. And then
Yeah, you can apply it right away, and then it simplifies in a nice way. So let me quickly try to do it that way. So it's greater or equal by arithmetic geometric mean. So do you know arithmetic geometric mean equals? Yes, greater or equal than 3 cubic roots. And by the way, it's important to write cubic root here. So somebody wrote just square root. So here we have. So let's just try to expand by linearity. The product here will be 1 plus A plus B plus C plus AB plus AC plus BC plus ABC. And this, of course, ABC is 1. And over here we will have
1 plus
1 plus AB plus AC plus BC plus AB squared C plus A squared BC plus ABC squared plus A squared B squared C squared. Now this thing is 1. And here we can extract factor ABC. So this is B, this is A, and this is C. So they're really the same. So this way you can also see that this is just C. Okay.
I did this problem and I made the mistake of, I tried to do it a different way,
Uh-huh.
and I made the mistake of thinking that division was associative.
There's no that. Yeah.
I don't know how I did that, but I did.
Right. So this one was just for this arithmetic mean, geometric mean inequality. There is also something called Cauchy-Schwarz inequality, which I will give a problem a couple of weeks from now on. So, but those two inequalities basically solve at least 50%, probably at least 80% of all inequalities you could see in an Olympiad. So you just
and then trivia.
so you just need to know those two. There's a third one which is very, very famous. The third one, if you have two ordered collections of numbers, like A's and B's, and you asked, so basically, how do you match them up so that the sum, the A1 B3 plus A2 B1 plus, like out of all such sums, right? You can match them up in different ways. Which one is the smallest one and which one is the largest one? And the largest one is when you match the smallest with smallest, etc. And the smallest is when you match like the biggest with smallest, etc. So this is a very famous inequality. It's not hard to prove, but so it also solves a lot of those questions. Okay, so I'll try to give more inequalities in the future. Now, functional equation, which nobody solved, which was surprising because I thought it was a really easy functional equation. So you're asked to find all functions f from z to z, from integers to integers, such that the following identity always holds. Okay, so I'm not sure how to explain why people didn't solve it, except they don't have much practice maybe with functional. So especially on IMOR, they really like functional equations. So it's important to practice. And a lot of them are solved by just kind of patterning around and plugging in small values and seeing what you get. So for this one, for example, let's see what we get when we plug in one of the numbers to be 0. What we get? We get f of n, f of minus 1 equals f of n plus 2. And we can solve for f of n from it. Right? We can rewrite it like this. F of n times 1 minus f of 0 equals 2 minus f of minus 1. And this really means that there are two cases. This must hold for any n. So there are two cases are, this thing is not 0. So the two cases are 1 minus f of n is not 0. In this case, you can just divide by it, and f of n will be constant. It's just always the same. Let's call it c. And then we can just plug it in and solve for c. So c plus c is equal to c squared plus 2. No, and this has no solution in z, right? We are asked for, well, I mean, even in real numbers, it has no solution. So basically, there's no such function. Therefore, the only way this can always be true is that if this guy is 0 and if this guy is 0. So, therefore, f of 0 is 1 and f of minus 1 is 2. Okay, so far this is not very strong because we found just a couple of values of it. Okay, so let's plug in something else to be something small. So for example, let's plug in m to be minus 1. What we get? We get f of n minus 1 plus f of minus n minus 1 is equal to f of minus 1 f of n plus 2. Which is, by the way, my f of minus 1 is 2. So you can just write this. 2 f of n plus 2. Okay, and the next observation is that those two are kind of symmetric if you change sign of n. So if you plug in minus n instead of n, we will get f of minus n minus 1 plus f of n minus 1, which is still the same thing, is equal to 2f of minus n plus 2. So since those two are equal, then those two also must be equal, which implies that f is a so-called even function. F of n is always equal to f of minus n.
Wait, if you plugged in what for the second one?
So here I just plug in, instead of n, I plug in minus n. Right, so we can put this. So in particular, this minus n minus 1 is this minus n plus 1. So we can rewrite this now as f of n minus 1 plus f of n plus 1 is equal to 2f of n plus 2. And now this is just a recursion which can be used to prove by induction what's the value, right? So we know that f of 0 is 1. We know, well, let's plug it here. So we get f of 1 is equal to, and we also know that f of minus 1 is 2. So 2 times f of 0 plus 2 minus f of minus 1, which is 2, right?
You already knew that because it was even.
Say again?
You already knew that because
Oh, yeah. Yeah. But then f of 2, for example, is 2 times f of 1 plus 2 minus f of 0, which is 5. And you can compute several such values, and basically you notice that f of n is equal to n squared plus 1. And of course, this is not a proof, but then you prove it by induction. So proof by induction, we have the base case, and f from this we solve. So f of n plus 1, assume it's true for previous ones, is twice n squared plus 1 plus 2 minus n minus 1 squared plus 1. And if we simplify this, we will get n squared plus 2n plus 2, which is n plus 1 squared plus 1. Again, we need to be careful because this just finds them for positive integers, but then we know it's even, therefore the same function works for negative integers. So therefore, there was nothing we did but just putter around and kind of plug in small values and see what it gives us. Okay. And let's do the last problem. The last problem had a lot of problems with people, first of all, figuring out the correct answer. So it's very easy to guess or figure out what the correct answer is. So let me remind you. So the problem is as follows. You have 20 teams, and they played some games such that among any three, two played already.
Can you just graph theory for this problem?
Yeah. So basically you have a graph on 20 vertices. So 20 vertices. And you have some edges, and inside any triangle you know that there is at least one edge which is there. For any three vertices, at least one edge is connected. And you asked what is the minimal number of edges in such a graph. Okay, so what is not hard to understand is that the following way is probably the best. You split them into 10 things and another 10 things, and you make all of them play with each other here, and you make all of them play with each other here. And then, of course, among any three, two will be in the same group, therefore they played with each other. And this gives you total of, 10 choose 2, 45, so 45 plus 45, which is 90 games. So the hard part is to argue that you cannot do less than that. And so here's what you cannot do. So, and I think that's what you did.
Yeah.
You cannot just say, our best possible way will look like this. We will partition our people into two groups and make all of them in one group play with each other and all of them in the other group play with each other. But you could ask for such thing, and then you would have like maybe k people here and 20 minus k people here, and you would say that the total number of edges is smallest one k is 10, therefore. So, but you cannot just assume that the answer looks a certain way. Maybe there is even better way, which looks nothing like this. Like it could be completely something different. So you need to argue that that's also not possible. So here's, here's one way to argue. So here's one thing we can notice. Let's pick one team, and there are some teams that played with, and there are some teams that didn't play with. I will denote it like dash lines. Okay, so this is a team. Let's call him X, and those are teams he played with, and those are teams he didn't play with. So everybody here must have played with each other. Otherwise what? Otherwise we would have a triangle where nobody played with nobody. So if the number of teams here is very big, then we are not doing it efficiently. So here's what we're going to do. Let's call this number X here, number of teams in this group, and then the number of teams here is 19 minus X, right? So total 20. And we want to make this number as big as possible. So for that, let's pick team X with smallest possible X. Meaning that pick a team which played as few games as possible. So every other team played at least that many as she did. Right, so this team played X games, and any other team played at least X games. Okay, so let's estimate how many total edges are there in this graph. So first of all, over here we must have, well, actually exactly 19 minus X choose 2, which is 19 minus X. 18 minus X over 2 games played between those guys with each other. Now let's estimate how many games those guys played. So there's X plus 1 of them, counting this guy, X himself. And each of them played at least X games, because that's how we chose X. That every team played at least X games. And we could or we could not be double counting, right? So if we are counting a game played by 2 people here, for example, then we are counting this game twice. because we counted once for this guy and once for this guy. But if we're counting a game, one of those guys played with this guy, for example, then we are not overcounting. We're just counting it as just once. So the worst we can overcount is by a factor of 2. Therefore, I claim that the total number of games played by this x plus 1 guys is at least x plus 1 times x over 2. Right? So assuming that, say, all are of this kind as opposed to this kind. If some of them are of this kind, then it's even bigger because we didn't overcount those. So the total number of games is at least this plus this. And now this is a quadratic expression in x, and it can be minimized. So first of all, it can be simplified. It looks like this: x squared minus 18x plus 18 times 19 over 2. And when is this minimal? Well, it's a parabola, right? So to minimize it, we find derivative, where derivative is 0. So minimal when 2x is 18 or x is 9. And then we just plug it in here, and you see we get 45 plus 45, which is 90. So we prove that this always is at least 90. On the other hand, 90 is achievable. Therefore, 90 is the answer. There are other ways to solve it, but one needs sort of to be careful not to assume something about the answer which was not proven. There were other people who assumed something which one just cannot assume it. Sort of. Okay, any questions about this? Okay, so let's finish our session.